Okay. So today we are discussing about diffraction. What do you mean by diffraction? Diffraction is nothing but bending of light. How can the light be bent? For example, there is one source. Here, you are taking any source here. From the source, light rays are moving forward. From the source, light rays are moving forward. And you have kept an obstacle here. And there is a screen. You will think that these obstacles are blocked and the light falls here. And you will think that only this part is bright and this part is going to be dark. Okay, this part is completely going to be dark, this part is going to be bright here. But it is not like that. Light bends. Light is going to bend. And the bending of light is because of secondary wavefronts. What do you mean by secondary wavefront? For example, if you take a source, from the source, wavefronts will move forward like this. This is called as a wavefront. So from the source, light travels in different directions. Okay, and at exactly equal points, if you join the points, you are getting wavefronts. You are getting wavefronts. When you try to block the light ray, light ray at this place, for example, at this point you are trying to block the light ray. So when you try to block the light ray at that point, what is going to happen? At this place, secondary wavefronts are created. So you cannot block the light completely, and wherever you try to block the light, their secondary wavefronts are created. What do you mean by wavefront actually? From the source, light rays are coming in different directions, and from this point of source to that point, to certain distance, you draw the points and join all the points, you will get a spherical shaped wavefront. Understand? So the spherical shaped wavefront you are getting, and these wavefronts move. When you try to block the wavefronts, then immediately secondary wavefronts will be forming, because of which light is trying to bend here. It is not going in a straight line, it is going to bend like this, and you will see that not only this part is bright, even this part is also a little bit bright, and brightness reduces from top to bottom. Brightness reduces from top to bottom. Even sound also diffracts. Sound also diffracts. How can I say that sound is going to diffract? If I keep a long pipe and start speaking towards you, it is not sure that only the people who are in front of the pipe is going to listen the sound. Definitely the people who are sitting aside, little bit aside, they are also able to listen the sound, because sound when it comes out of the pipe, it going to bend. It starts bending here. That process is called as diffraction process. And even from the sun, light rays are coming. That is also diffraction process. For example, let me discuss one concept here. Okay. So in this diffraction, you are going to see sunrise and sunset is going to be red in color, isn't it? So what is going to happen? For example, this is a hill, okay, and you are standing at this place. You will see that early morning you are going to see a sun which is red in color. This sun is red in color, and directly you can see the sun. There is no stress to your eyes. The shining of the sun you are not going to see. You will see a red ball, let's say. And what is that red ball? It is not an actual sun, it is a diffracted image of the sun. It is a diffracted image of the sun. Original sun will be at this place, okay. What is going to happen? Light ray, when it starts moving, it bends like this. Okay. And now you are going to see sun at this place. And why there is red color in sun early morning, during sunrise, during sunset also red color. Okay, so at the evening also you are seeing a red ball of sun which is red in color. Why? What is the reason behind that? Because actually original sun is going to set already. Already it has been set. But the image of the sun you are going to see red in color. Why red in color? Because bending of red color is least. For example, if you consider a prism, white light is passing here, you are going to get 7 colors, isn't it? In 7 colors, this is going to be violet and this is going to be red. Red is having less bending. That's why you are going to see red color sun when sunrise and sunset. Where that is not the actual image of the sun. It is not an actual sun. It is a diffracted image of the sun which you are going to see during sunset and sunrise. That is called as diffraction pattern. So if you observe this diagram, if you are observing this diagram, from the source you are getting wavefronts. There is a slit here. This is called as a single slit. This is called as a single slit, and this is called as single slit experiment for diffraction. So there is a small hole here. You will think that light will come and fall at this place. Only this much part is going to be bright, but it is not so. Light, when it passes this obstacle, a small slit, it is going to bend because of secondary wavelets are created. Energy can neither be created nor be destroyed. If you try to block at that point, secondary wavefronts are created. Secondary wavefronts are created at that point. That's the reason why light ray is going to bend here. Got the point now? So you will think that only this much part is going to be bright, but it is not so. The part of brightness goes on spreads, but you will observe one thing. This is having more brightness, whereas this part brightness slowly decreases. The intensity of brightness decreases as you go wide. Okay, so this is the first image. After that, you see the various images which I have drawn here. See, the bending of light completely depends upon the wavelength of light. If the slit size, what is this D? D is nothing but the size of the slit which you are going to consider. If the size of the slit is greater than the wavelength of the light, if the size of the slit is greater than the wavelength of the light, then there is no bending of light. Diffraction does not take place. That is the condition you have to remember. What is the condition? If wavelength of the light which is coming through the slit is less than the slit size, then there is no bending. If the wavelength is less, okay, so if wavelength is less, if it is much less, no bending. Little bit less, there is a slight bending of light takes place, because at this point secondary wavelets are created. So wherever you try to stop it, secondary wavelets start creating. That is a very magical thing is happening here. So if wavelength is much greater than D, then bending will be maximum. Bending of light will be maximum. Wavefront's radius will be less, more curved, less radius. So this is the part which you are going to see here, and this pattern is because of diffraction. In diffraction also there are of two types. One is Fresnel diffraction, another is Fraunhofer diffraction. What do you mean by Fresnel diffraction? Okay. See, if the source and the screen, what is this? This is going to be screen. When the source and the screen is having a finite distance, a very less distance, then what is going to happen? After crossing the slit, the light falls in the form of fringes. So light falls here, it bends like this. It doesn't mean it is going to bend only in this direction. It bends like this also. Here also you will get series of dark and bright bands. So you are getting bright band here, and the light ray even falls at this place also. So here also you are getting bright bands. So this is bright band, this is dark band, this is bright band, and this is dark band, and this is bright band. A series of dark bands and bright bands are seen. That is explained by Fresnel's diffraction pattern. And this is applicable. This diffraction pattern explained by the scientist called as Fresnel, it is applicable only when the source and screens are at finite distance. But the pattern of diffraction is not at all clear. You can't see the clear pattern of fringes. That is a demerit here. And that's why this having a lot of demerits. it is not considered. So the main diffraction pattern which was considered is Fraunhofer diffraction pattern. So in this Fraunhofer diffraction pattern, what is considered? Let us see here. Okay. So what is happening in Fraunhofer diffraction pattern? This Fraunhofer diffraction pattern is applicable if the source and the screen are at infinite distance. If the source is sun and screen you are going to consider here somewhere. As the source is at the infinite distance, the light, you know, it is going to spread in different directions. Light is going to spread. That's the reason why we have to collect the light here. You have to collect the light, focus the light in a parallel path. So what are you going to do? For example, you are taking one source at this place, which is a lot of distance away from the screen. Like take one small bulb. But the distance between the slit and the bulb is large. And from the bulb, light is going to diverge. Diverge means moving away from one point. Moving away from one point. Converge means moving towards one point is called as converging. Okay. So here diverging light rays are being made parallel by using one lens, so that light rays become parallel when they pass through the slit. And after passing through the slit here, again one more lens is taken so that this parallel beam of light ray get converged and meet a certain point here. That's why here also on this slit, if you observe, this is going to be a bright band here which is formed because of Fraunhofer diffraction. This diffraction is having a bit more advantages compared to Fresnel diffraction because of this lens. There is a clear pattern observed of diffraction. A series of dark and bright bands you can see in this process. So this is called as Fraunhofer diffraction. Next, if you observe, this is the slit. This is a single slit experiment. From the source, wavefronts are coming. What type of wavefronts you are seeing here? These are called as plane wavefronts. So when you get plane wavefronts, when the source is at infinity, you will get plane wavefronts. Let me show what is the meaning of this plane wavefronts. I will show you on the board here. What is the meaning of plane wavefronts? See, when you consider any source at this place, first you will see that the wavefronts are curved in nature. But as the distance is passed, as the distance increases from the source, this curvedness will decrease. The curved path becomes a little bit less curved and radius increases. If you take the smallest part of this, it is just like a plane wavefront. As the source is at infinity, these plane wavefronts are entering. And you know, this is called as the single slit. This is taken as A, and A is called as aperture. A is called as aperture. What is the meaning of aperture? Aperture is nothing but if you keep a lens over here. Aperture is nothing but the part of the lens which is exposed to light is called as aperture. The part of the lens which is exposed to light is called as aperture. In double slit experiment we have taken the distance as small d, whereas here we are taking A. A is nothing but aperture, where aperture explains that only this much part of the lens is exposed to light. So when you keep a lens, the light is definitely going to converge. And if you observe the pattern of diffraction here, at the middle there is principal maximum, or it is also called as central maximum. So this is having more brightness, maximum brightness, and again this part is taken as dark fringe. Understand? First dark fringe, and this is called as first bright fringe, and this is second dark fringe, second bright fringe. This is called as central bright fringe, or it is also called as principal bright fringe. Understood? So in this way, slowly the intensity decreases from middle to the extreme points. Okay, so this is about the diffraction pattern. So now, if you understand what is explained in this case of single slit experiment. In this single slit experiment, this is only the slits here. This part is open. This is open part of the slit here, which is taken as distance d, or sometimes you can also consider as small a also. It can be considered as small a also. So once the light ray enters, I just told you before that light is going to bend a little bit because of diffraction pattern after crossing the slit. Why? Because secondary wavefronts are created at the slit here. So this light ray, when it falls on the lens, this is called as convex lens. It is also called as converging lens. It can converge the parallel beam of light ray at certain points. Oh, so direct light ray falls at this place, giving rise to a bright band at the middle. Direct light ray which falls on the lens is collected here, and you are going to get the central bright band, and it is also called as principal bright band at the middle. Okay, so what is going to happen here if you observe? If you observe, the parallel beam of light ray falls on the lens. It is falling at the central, and this is some other band. That band can be dark band, that band can be bright band also. So we can derive now. We can derive the equation. Let us see what is going to happen. First thing is, what is this going to be? This is going to be the path difference here. Extra distance traveled by the light ray. So this is angle theta, and this is also going to be angle theta here. Okay. How much it is tilted? How much it is tilted? The same angle it goes to be taking place here. This angle and this angle is also going to be same here. So if you observe this pattern here, now if you consider this triangle A, B and N. Okay. This is A, B and N. In triangle A, B, N, if you consider sin theta here, you can write opposite side delta x by, this can be taken as adjacent side. Okay. So this is going to be opposite sides by adjacent side. So therefore, you can write this as equation number 1. And the next equation is tan theta. If you consider tan theta here, the opposite side is going to be yn. The opposite side is going to be yn. And the adjacent side is going to be the distance d here. Okay, distance d here. So from the slit to the source, from the slit to the screen, the distance is taken as capital D. Whereas from the lens to the screen, it is taken as f, which is called as focal length. Because parallel beam of light ray is just focused on the screen. Okay, so this can also be taken as focal point. It is called as principle of focus. So distance from the lens to the principle of focus is taken as focal length here. What the point now? So this is about sin theta and tan theta. Tan theta is equal to opposite side by adjacent side, which is taken as capital D here. This is equation number 2. Next, if you consider if theta is very small, you can write sin theta is approximately equal to tan theta. Sin theta is approximately equal to tan theta. Then, if these two angles are very small, then what are you going to do here? You can write yn by capital D is equal to delta x by a. Okay, these two are going to be same here. Then you will write yn is equal to delta x into capital D by small a. So this is the equation which you are going to get. Now this can also be written like this. This can also be written like this. What is that? A sin theta is equal to, A sin theta can also be written as delta x here. A sin theta is also written as delta x. Here it is completely different than Young's double slit experiment. So for example, for maxima you will write A sin theta is equal to n plus half into lambda here. Okay, for maxima n plus half into lambda you are going to write, whereas for minima you write A sin theta is equal to n lambda. It's completely different. Whereas in Young's double slit experiment, you observe that you have written d sin theta is equal to n lambda for maxima, and for minima you have written d sin theta is equal to n minus half into lambda. It is completely different. What is the reason behind that? That is very important. Why is it so? Why is it so? Pass. Okay. So next, why we consider for maxima, for minima, we consider that delta x equal to n lambda. Why is it so? And for max, okay. So here, what is the reason that for minima, if you consider at this place, delta x is considered to be n into lambda? What is the reason for that? Here, to get minima, for example, if I draw the screen here, this is going to be first minima. So here, if you observe the screen and the slit here, you know this is a slit. To get minima, the screen and the slit gets divided into two equal halves automatically. The slits is divided into two equal halves automatically, and in the upper half you will get a wave like this. At the lower half you will get the wave in this way, which is having destructive interference. The upper wave and lower wave is having destructive interference. The crust of the upper wave is falling on the trough of the lower wave. So, what is the meaning of this? What is the path difference between these two waves? Can you tell me? Path difference is going to be lambda by 2. Why is it so? Why is lambda by 2? I will tell you here. Just see. So, for example, if this is the wave, okay, another wave is like this. What is the meaning of this? This is 0 to pi. It is starting from pi here. Okay. So, pi to 2 pi, isn't it? From 0 to pi, this is starting from pi to 2 pi. So, what is the phase difference? Phase difference is pi. And what is the path difference? The next wave which is starting from here is starting from here. So, what is the difference between these two? Path difference is going to be half of the wavelength. The upper wave and lower wave is having path difference of lambda by 2. Half of the wavelength. I think you understood. So, here, if you observe why minima is formed, further explanation is there. See, automatically slit is getting divided into two parts, two equal halves. And here, the upper wave and lower wave is having a path difference of lambda by 2. Are you seeing lambda by 2 here? The path difference is lambda by 2. Again here, path difference is going to be lambda. So every step, lambda by 2 is increasing. So now, here, path difference at this place is going to be how much? Here it is lambda by 2 between these two waves, and here if you come, it is going to be lambda. Path difference is going to be lambda. Understand? This is for first minima. For example, now I am discussing about second minima. So what is this? This is going to be principal maxima, which is at the middle. This is first minima. This is first maxima, and this is going to be second minima. Why the second minima is formed here? Okay, this is principal maxima, first minima, first maxima, second minima. So second minima is formed because the distance, the slit is automatically divided into 4 parts. And if you observe here in these 2 parts, the crust is falling on the trough. So destructive interference takes place. Destructive interference creates dark band, dark fringe. So these 2 waves completely destroys. So darkness will be outside. Now the second minima is formed because the same is the distance between the slits. Just it is shown like this to understand. The same is the distance between the slits, but the slits are getting divided into 4 equal parts, and every step the path difference increases by lambda by 2, 2 lambda by 2, 3 lambda by 2, 2 lambda. Therefore, here path difference is going to be how much? 2 lambda. Path difference is going to be 2 lambda. Here, in the upper part you are getting this wave. In the below part you are getting this wave. Both are getting destroyed. Destructive interference takes place because crust is falling on trough. Next, here also one wave is formed like this. another wave is formed like this, because the path difference between first section and second section is lambda by 2. So therefore destructive interference takes place between these two pairs. Destructive interference also takes place between these two pairs. So outside nothing will be there. Completely brightness is destroyed. That's the reason you get second minima. Is it clear? So minimas are formed because distribution between the slits is even number. 2, 4. Now we shall discuss how maximas are formed by another example here. So this is the discussion about minima. Then what about the maxima, if you observe? So now if I take a screen here, see it. If this is a screen you are going to take, so what is this going to be? This is going to be central maxima, first minima, and this is going to be first maxima. This is principal minima, principal maxima, first minima, first secondary minima, first secondary maxima. So I am explaining now first secondary maxima. How is it going to form? So to form maxima here, the distance between the slits is automatically divided into even numbers. So it is divided into 3 parts here. As it is divided into 3 parts, the path difference here, first part and second part is lambda by 2. And this part is 2 lambda by 2. And this is 3 lambda by 2. So here, delta x is going to be how much? 3 lambda by 2. Then what is going to happen here? The first part forms one wave and the second part forms another wave. If you observe these two waves, destruction takes place. These two waves are destroyed. But finally, one unpaired wave is alive. It is not getting destroyed. Because even pairs. So 2 pairs are getting destroyed. And this is a bachelor. Do you follow or not? And you are going to get a first maxima because of this only this wave. Got the point now? So therefore, path difference increases by lambda by 2, lambda by 2, lambda by 2. Finally, path difference is 3 lambda by 2. Okay. So the next part. Okay. So this is the part which explains about second maxima. So because of this you are getting second maxima. Okay. So what is going to happen here? Just see here. I told you to form a maxima here, the sections are formed into odd numbers. So it is divided into 5 parts now. The distance between the slits is same. I mean the aperture is same here. Gap is same. But it is divided into how many parts? 5 parts. So first part gives one wave. Second part gives one wave. They both get destroyed. Next, this part gives one wave. And this part gives another wave. Because of destructive interference, this pair is also getting cancelled. But if you observe, this pair is a bachelor. It is a single wave. And the brightness second maxima is because of this wave only. But if you observe, in the previous case, 1/3 part, this is because of 1/3 part, no? And this is because of 1/5 part. 1/5 part only you are getting this one. So this is because this brightness is because of 1/3 part. This brightness is because of only 1/5 part. Therefore, as you go from central to away, brightness decreases. Is it clear? Brightness decreases. Intensity decreases. Intensity of central maxima is maximum compared to the first maximum. And intensity of the first maxima is less than this one. And second maxima is less than again this one. And if you go further, you will get only the brightness because of 1/7 part. So slowly intensity is going to decrease. I think it is clear. Okay. So in this way, you are going to get path difference. Delta x is equal to 5 lambda by 2. Then in this way, again, the next part will become 7 lambda by 2. 7 parts divided. It is going to be delta x is equal to 7 lambda by 2. Therefore, you can write in general, path difference can be taken as n plus half into lambda, where n equal to 1, 2, 3. For first maxima, In the place of n, you will write 1. So we are getting 3 lambda by 2 previously I explained. In the second point, there is second maxima, you have to substitute 2. You are getting 5 lambda by 2 because 2 plus 1 by 2 is 5 lambda by 2. In the third maxima, which is further above, you have to substitute the value of 3 here. We are getting 7 lambda by 2. So this is going to be the general formula for maxima. And what is the path reference for a minima? Only n lambda, isn't it? Okay, so this is the problem actually. So after that we can go for one more concept here. So this is the beautiful diagram which shows how you are going to get the maxima and the minima over here. So central, maxima, primary, secondary, understand? So this is maxima, minima and like this. This is you are getting a series of maxima and minimas with decreasing intensities. Okay, so there is decreasing intensities. Then we should discuss about one previous year problem here. Okay, so this is a previous year problem. What does it mean here? In diffraction pattern due to a single slit experiment of width A. So what is the width of the experiment? You can just see here, width A here. Then if you observe the question here, the angle is 30 degrees for first minima. So this is going to be the first secondary minima where the angle is given as 30 degrees. He is asking us to find out the first secondary maxima is observed at an angle of how much? That means this is the first minima and this is the first secondary maxima. This angle theta you have to find out. So first of all he has given, and I told you that path difference A sin theta is equal to n lambda. Why is it so? I told you that sin theta is equal to opposite side. What was the opposite side here? Path difference was the opposite side and this was the adjacent side. From where did we derive this one? From this concept we have derived. This was the path difference delta x. This is theta. Okay. And what was this? This was aperture, isn't it? So I have written there sin theta is equal to opposite side by aperture A. Okay. So what are we going to write now? Sin theta is equal to delta x by A. Okay. So here delta x. What is this actually? So this is for minima he is telling. I told you that delta x is equal to n lambda for minima. So as it is the first minima, you have to consider n equal to 1. N equal to 1. Instead of n I have kept here 1. So lambda by a I am writing. And it is given that the angle is 30 degrees for the first secondary minima. I have written the angle 30 degrees here, isn't it? So sin 30 is equal to lambda by a, which is equal to sin 30. The value of sin 30 is 1 by 2. So indirectly we get the value of lambda by a as half. And the second part of the question is telling that find the angle made by the first secondary maxima. So this angle theta one you have to find out.